Okay, good morning, everyone. Maybe good afternoon in in Denmark. So today we have with us Professor Joseph Guerrero, who will present his topic and his presentation related to the microgrids. So thank you. You have the floor is yours. Thank you for accepting this invitation.
Yeah. Thank you very much, Hanane, Professor Hanane, for this opportunity. Can you see clear my screen?
Yes, exactly.
Yeah,
yes,
thank you. So I'm going to make a presentation to talk a little bit about microgrids. You can also find more information here in our Center for Research of Microgrids in the Department of Energy Technology of Aalborg University. So here you have also this is the new website. Yeah. I want to start with a foreword. This is from a person who's very much involved on mindfulness, John Kabat-Zinn. He said, "The little things, the little moments, they aren't little." Yeah, and this is related to microgrids when we think about little world. And I'm going to introduce also in this presentation some ideas on microgrids in the space. So that's why I started also with this picture. Something about me. I was very curious about electronics from 10 years old and very active psychologist, teenager. And my major is on communications. So I'm sorry if I say something stupid when I talk about electricity, especially electric power systems. And for me, one of the major things are also music. So this is very important also regarding the idea of creation. And the other one is to create, of course, products for the industry that can be useful. No? This was, for instance, after my PhD, right now, those ideas are in some products, UPS systems that you can buy. Some things about success, no, and failures. People is very much focused on success, but I will say that these are some words from Michael Jordan saying that the key of success is failure, right? And he summarized his career something like this. I missed more than 9,000 shots in my career. I lost over 300 games and so on. Yeah. So I think that's really a way of living, and I really align with his words. Also, I think that some of his words about limits, never say never because of limits, because fears, because those are often just an illusion. And also you must expect great things of yourself before you can do them. Fantastic. Also, if you think about the tigers, for instance, this is a Bengal tiger. It needs to take 10 attempts to hunt a deer before it can hunt it. And I think that's very important. I don't think that the Bengal tiger complains or gets frustrated or thinks, why me, right? So this is about human beings, and I will connect this also with our intelligence, because I think it's important to understand our intelligence to see how we put in our microgrid system the intelligence. First, about microgrid concept. Some people, when you talk about microgrids, think that is only about electricity. And we can see now people also applying those concepts, for instance, in water. They call micronets. So the concept is kind of similar. You take the water, maybe from fluvial, and then you store and you consume as closer as possible. And you can see similar things also with food, when we try to eat the food that we are producing as closer as possible. We call this also 0 kilometer foods. So I will say that this microgrid is more a concept than really, or a philosophy of doing things, more than really something that have a definition. And of course, we can see that we have more and more appliances in some houses. So you could have also photovoltaic systems and electric vehicles. But what is clear is that more sensors are also coming. No? And ideas of having energy communities are already there. But also you can see in some other poor countries. For instance, this is from Nepal. And right now we are starting also some other projects in Ethiopia, Indonesia, and also Madagascar, in which having microgrid systems are necessary, but because you have very poor houses, maybe we talk about 100 watt peak. Yeah, 100 watt, and people can survive with that. Maybe connecting laptops, cell phones, and so on. This is about our team. So you can see we are around 50 people, and thanks to them, I can make this presentation today. Otherwise, it's almost not possible. So this is just, and this is about our laboratories facilities. So in our laboratory facilities, what we have is power electronics converters with some digital signal processors, and we create microgrids. Those are 10 kilowatt microgrids, and in that case, we also have, these are GPS systems, which also we can use. And another important thing is how we test the things that we develop. This is one of the cards that we are developing right now with Zonen, which is a battery manufacturer. And the idea is that we don't connect our control boards to real systems. We have a real-time simulator. We develop those boards for them, and then we send them the codes, and then they can test with the real devices. And I will say that this is very important to make a lot of tests before and without, let's say, crashing anything or or damaging some of the equipment. Those are the research frameworks that we have in our Center for Research on Microgrids. One is multi-microgrid clusters, so a number of microgrids interconnected between them. The other is digitalization with digital twins and IoT. Then we have also a lot of activities regarding maritime microgrids, electrification in ships and ports. And last, this is what one part that I'm going to present today is about the space microgrids. So how we can go on with electrification also in the space systems. First, many people talked about artificial intelligence, but I'm not sure that we know exactly how our brain works. Indeed, today we know that in our minds we have about 80,000 million neurons, but also recently we discovered that in the heart we have 40,000 neurons. Now it's not strange for us. And then we have around 500 million neurons in our digestion system, exactly the same as the number of neurons that a cat holds. So I think that's really a distributed system. And you can see also when some feelings, and it has been also sensed when you have some feelings of, for instance, love, hate, even trust, then some of these neural networks, especially those that are in the heart, are activated. And then the digestion system is also very important because depending on how you are feeding yourself, also you have bacteria that will affect all these neurons. And this is more connected also with emotional states, right? So now we can see this, maybe feelings, maybe emotions here, and then the brain. So it's really a distributed system. Yeah. It's not true that we use only 5% of the brain. Some people said in the past, we use 100%. However, simultaneously, we only can use 2%, which is 4 watts. We have to think that our brain is electronic. So only 4 watts. And this is because of the limitations of glucose and oxygen. However, even though we use 100% of the whole brain, normally we use similar neural network paths. And this is why some people feel that they cannot change. Yeah? You have some habits and you cannot change it. It's not true that you cannot change. Indeed, we have right now neuroplasticity. So this means that you can make new connections, but because you used to use the same, and then it's more hard. You can do it, and we can discuss this if you want after the presentation. Then inside the brain itself, in these 86,000 million neurons interconnected with synapses between them, what we have is several layers. Yeah, here we have again 3 layers, right? So the first layer is the reptilian brain, which is the first that was developed with the reptiles, and these have 500 million years. And this is a part of the brain more action-reaction, which tries to find also possibilities and opportunities for you, and it's also regulating this part. Many of our body parts that need some automatic things, like which is our temperature in our body, also our heart beats, etc. So many of these things comes from this cerebellum part, and this becomes the reptilian brain. Yeah, indeed, right now there are many people studying what is called also neuromarketing, and they are trying to study the brain to sell better the products. And it's really the way that you are buying, it's just using the reptilian brain. Then we have the limbic brain, which is the one which is more emotional. So emotions, a lot coming from here. And it has been developed with the mammals. So all the mammals have this limbic brain, and it has 200 million years. So a lot of emotions are also coming from here. And this is why you can for instance, love your dog, and he will give you love back, but don't try to do the same with a snake. It will basically don't work, right? And then we have the more new thing, which is the neocortex, which have 100,000 years. And I will say that this is the rational part. And I will say that this is very amazing because especially the prefrontal part is the one who allows us to project us into the future, make plans, come back to the present moment, and take decisions. And I will say that a lot of animals cannot do that. So this is specific for human beings. However, you can see here, because of the number of years, finally, a lot of our decisions are coming from emotions. Yeah, from the limbic brain. And then it's the rational part which comes with the justification of the decision. So a lot of our decisions are just coming just because of feelings that are placed in this area of the brain. Yeah, I think that's very interesting to see these three levels of control, which sometimes are, one is fighting with the other. Yeah, sometimes emotional part is fighting with the rational part. Maybe the reptilian say, hey, you have here a huge opportunity, and it's really amazing. The other thing is about stress. So right now we know that moderate levels of stress are good. However, because you can even generate some of these neurotransmitters like dopamine or noradrenaline, which we know today that it's very good to have learning, motivation, etc. But if you surpass some level, then you arrive to fatigue, exhaustion, and even burnout. So also moderate levels of stress are very important. Right now, I will say that we have people with high levels of stress, and then this creates a lot of problems. If you want, later on, we can talk also about how this affects our ADN structure and how this can produce a lot of diseases. Then about trust and fear. This is from another study made, I think, a couple of years ago, in which neuroscientists detect that the same areas of the brain which are activated when you trust are the same that when you have fear. So this means that you cannot feel trust and fear at the same time, right? So that's something very interesting to look at. And the other one is about the empathy systems. This is, I will say, for instance, the emotional empathy. It's like when you see someone cries and then you want to cry as well. It's because you have enough neurons making mirror. This is what is called also mirror neuron system. And yeah, I will say that the research in this area is really amazing. In the last 5 years, we know things that we never knew before. So I will say that even for our daily lives, this is very important to start understanding neuroscience. Another interesting thing, this comes from the Hertz Math Institute in Germany. They studied the communication between the heart and the brain, and they come out with something really amazing. there is more communication information coming from the heart to the brain than from the brain to the heart. So sometimes I wonder myself, who's the boss here, right? And also the heart, we know recently that generates also hormones. So also generates oxytocin, which is connected also with these feelings of love, trust, and fidelity. And it's the same hormone that, for instance, women produce when they have to have a baby. So I think that this is also an amazing thing. And the other one is this other hormone, which is controlling stress. So from the heart, we really can have a lot of control to the brain, right? Yes. And then the other thing is like just looking at the coherence between the brain and the heart, we can see amazing waveforms like that. Some people think that heart rate needs to be constant. Normally they give you a number. Yeah, this is the number that you have of your heart rate, but it's really not constant. What your body tries to make is your blood pressure constant. This is very important. And then the heart rate is changing to allow you to have this blood pressure constant. And then this means that it's changing all the time. You can see here the heart rate waveform when we have feelings of incoherence. So this means frustration, anxiety, worry, irritation. You can see non-periodic waveform and a lot of harmonics here. Yeah, however, when we are in coherence between the heart and the brain, we have positive emotions, appreciation, love, and courage. You can see that this almost sinusoidal waveform, right? I will say that this is really something amazing that we didn't know in the past. And the other interesting thing that is also that the heart have an electromagnetic field 5,000 bigger than the brain and can be measured in more than 3 meters. And also there are some studies in which they put some people together and their hearts can be synchronized. For instance, in the case of lovers or some people singing some songs, they could sometimes match also the synchronization. And this makes a lot of sense because we are social entities. Yeah, also some studies has been made also between dogs and owners. And yeah, I think that's also another amazing thing to see how they are synchronized in terms of the heart rhythms. Let's see what happened with our microgrid, because also here in our microgrid, we need kind of a control. And well, right now, you know all these things. And one of the first things that we wonder when we talk about microgrids is, should we go for AC or should we go for DC? Maybe some of you knows about the fight between Nikola Tesla and Thomas Edison. And I will say that apart from these problems, maybe caused by the limbic part of the brains, one of the facts that why DC was not successful at that time, it was exactly in this sentence said by Tesla. He said, direct current may find for cities when buildings are close together, but most of your country, talking about United States, is empty spaces. Only high voltage can span distance. You are not thinking long term. Yeah, but now it's twisting the thing again, and we are rethinking that we need to produce the electricity closer to the consumption points. So that's why exactly what was a fail at that time, it's now something that could have success. At the same time, you can see also some products in the industry that can operate for microgrids. So we are not, as in the past anymore. I will say in the last 10 years, we have a lot of products that allow us to implement microgrids. So maybe 20 years ago, we could say, oh, it's very difficult, nothing. But right now we have all the technologies available. Yeah. So if you can see, for instance, this is from SMA, it's a bidirectional DC-AC converter. So you could have some parts on AC and some other parts on DC. Yeah, and at the same time also accomplishing what we call also frequency regulation. I will talk also about this later, but you could have both in blue DC and in red AC. And then talking about frequency regulation, also you can see that many of the controllers that we are talking today, like having frequency droops or voltage droops, they have been also implemented. Maybe some companies comes with even patents and so on, but I will say that this is in public domain. And the idea here is to try to make your converters work as a synchronous generator. Yeah, I will show you later an example. So you can see here, I tried to find also some examples with other products which are available, like for instance, Fronius. This is from Fronius, just a PV inverter. And then we have other products that allow us to connect battery systems or diesel generators. This is from Victron. So they are indeed making to make really a match. So you could use this converter to inject all the power that you need, and you can use this other converter to absorb the power or to put the power back. Always having also in mind that we need to comply with the frequency regulation, which I will talk later. So today we have already these things available in the market. We have photovoltaic systems which are able to be connected to the grid. And you can have a number of control loops like current loops and so on. And we have the same when we think about both batteries and PV panels. So if you think about the battery, normally you will try to fix the voltage here. That's why you have a control voltage loop and a current loop. But when you think about photovoltaic panels, what you have is an algorithm to find the maximum power to be injected into the grid. Yeah. In the past, these two applications were totally separated. But I will say that today we have already in these applications possibility to match together. So this means that if you think about a microgrid in which we could have a battery system like in the middle, and then we could have solar panels, and we could have some loads. Right now, our inverters that are connected to batteries, when the state of charge is very high, they are also pushing up the frequency. So when you push up the frequency, our photovoltaic panels knows that the system maybe is starting to be overload, so we can decrease the power, and they find a common operation point. So as I said, this is something that we find today in our products. So you just find, for instance, in the case that I showed you before, from SMA, they have a product called Sunny Island, another Sunny Boy, and they match together thanks to this frequency regulation. Yeah. So basically here what we do is this is from a solar panel. When we feel that the batteries are having a state of charge very high, then we increase the frequency and automatically our inverters will move outside the maximum power. Yeah. So this is something very nice to see that this is possible. And right now, I think that our work is to look at what is existing and see how we can implement in real sites. Yeah. So for instance, another important thing is that when you think about a microgrid, you have some generators, maybe solar panels, which we need to inject all the possible power. And we could have also storage here in the middle. When we are connected to the grid is fixing frequency and voltage here. But if we are, for instance, disconnected from the grid, we need to maintain the voltage and the frequency by some of these elements. And normally the elements which will maintain voltage and frequency will be the energy storage systems, because they are present all the time. Maybe you have photovoltaic panels, during the night they are not available. So then it's, in general, we try to fix voltage and frequency. So there are two ways that your microgrid can go to island. One is to have a pretty plain islanding operation. So this means that I see that there is some problems with the grid, so power quality is not good enough, so I decide to disconnect. And then this is easy and safe. However, sometimes we have blackouts, and this is what we call also non-plane islanding operation. And when there is a blackout, we need to detect that really we are disconnected from the grid. Otherwise, imagine a guy who's arranging some parts of the grid, and this guy just disconnect upstreams, and the guy thinks that nobody's injecting power. Then we could kill this guy, or we could damage a lot of equipment. So that's why it's very important to detect that we are in island very fast. Yeah. Some example of microgrid operation. This is placed in China, in a small town called Xinxia. And in this small town, what they have is a 100 kilowatt of genset. And then they have around 70 kilowatt of solar panels and 80 kilowatt of battery. It's disconnected from the grid because, as you can see here, it's in a very remote area. So this is a little bit about the numbers. Yeah, I know that now they are trying to also get rid of the diesel generator, which is something very important. But in the past, it was like this. No, they have a peak of load of 90 kilowatt at night time, and well, let me show you. They have this extreme behavior because people basically use to work in agricultural places. So it's just when they come back home that energy production increases. So in dark blue, you can see how it's this. This is the noon, yeah, and you can see that it's more or less around 50 kilowatt, 40 kilowatt, and then it's around 6 o'clock, 7 o'clock at night that produce this peak of power of around 90 kilowatt. Yeah. And then here in pink, you can imagine that this is the photovoltaic generation. Yeah, here is the noon. And then, of course, because they have this difference between the, let's say, the pink and the dark blue, they have the battery system, which is, you can see, plus minus 40 kilowatt. And then when they need huge amount of demand, then they need to start the diesel generator as a backup. So you can see, for instance, that before the night occurs, more or less 5 o'clock, they already start the diesel generator for the night. And then you can see that it's not exactly matching. So it's the battery who's supporting it as a peak, right? So I will say that this is very illustrative thing. Yeah. And you can think also, if you go for 100% of renewable energy, which then you can, of course, have bigger size of these batteries, but still you have to design inside the maximum power exchange of let's say the system. No, I think that's a very good illustrative example. Yeah, so that means that we need one of our elements, in our case the battery system, to fix a voltage and frequency, so to work as a voltage source, and then all the other elements that are injecting or generating electricity, like current sources. And then we have the loads, which are also kind of current sources, right? What happens when we have a number of elements, for instance, number of battery systems that are trying to be connected in parallel, then small differences in phase, frequency, or voltage produce huge currents flowing from one converter to another. That's why we need to implement some control loops inside to regulate it. And what we use is those equations, which are the transmission equations, which they told us that small changes in frequency and power angle will produce high differences in active power, while the voltage is affecting more reactive power. Yeah. That's why if you take a look on how a synchronous generator works, we say that difference of power between the generator and the load produces variations in frequency. And this is according to J, which is the inertia of the system. Yeah. So if you want to look at, but without equations, just, okay, one shot, you can see that when we have an increase of power, from the generator, the frequency is dropping, and then it's stable again, but you have a, let's say, a static frequency deviation. Yeah, and it's because of this phenomena that we are able to make our generators to be, let's say, friendly with the grid, because the grid is full of synchronous generators. So what we want to do is also that our converter operates as a synchronous generator. And what we do is we put the machines inside the equations of this machine. We program the algorithms in what we call virtual synchronous generator. And those equations are regulating the power converters. However, in many projects, it has been shown that you still need energy storage to provide inertia. So finally, inertia is coming from the machine, and you need kind of inertia, maybe kinetic, like flywheels, or if you have a huge wind turbine also, you will have inertia there, or it could be also battery system, especially when you think about photovoltaics, which they don't have inertia. I'm going to show you just one example to see how all the synchronous generators are synchronized in the grid without having any communication between them. I don't know if you know what is that. Those are metronomes. Because I'm a musician, then I use a lot these kind of things. Yeah. Right now there's a lot of electronics also, and even in the cell phone you have apps, but it doesn't work with electronics, as you can imagine. You have a big mass here down, and this and what we did here is we put, this is, I think it's an experiment made in Japan. 1, 2, 3, 4, 5, 6, 8. So 32 metronomes together in a platform which is floating. So it's a floating platform. Yeah. And in purpose, what we do is we start them out of phase. Yeah, you will see. I don't know if you see them. Yeah, they are out of phase. Yeah, out of phase. Okay. With the time, what happened? With the time, all of them are synchronized. Maybe here there is one crazy one. No, don't worry. Now it's fine. So this is exactly the phenomena that we have with synchronous generators. So you can imagine that this mass is like the inertia of our synchronous generator. And this table, this floating table, are the cables, the electric cables that couple all of this system electrically. Yeah. So a very good example that we don't need to communicate anything between synchronous generators in our wall to be synchronized. So all the synchronous generators that are connected to the system are naturally synchronized. And this is amazing. And this is because of the physics. Now what we do is we take the same idea from the physics and we apply to a system in which you don't have inertias. So basically here, what we do is we implement this with a digital signal processor, and we implement those inertias to emulate the behavior of synchronous generators. So basically, when we increase the power, we decrease the frequency. This is something you can imagine. If you go for a run, for instance, you are running and you have some speed. If someone gives you, for instance, a bag, which is very heavy, of course, your speed will go down, right? So this is inertia, right? The point is that, imagine that one is running very fast, the other less. Okay, we are just putting more stones to the back of the first one, and then it will go down, the other will speed up, and they will find a common frequency of operation. Indeed, the whole system have only one frequency because all of them are coupled. Yeah. You can also export these ideas when you have generation and storage and so on and so forth. Yeah. So this means that when we have a microgrid system and it's suddenly disconnected from the grid, the frequency here will depend on the total amount of loads that you have. So this means that, for instance, if I have more demand than generation, the frequency will go down. However, if I have more generation than consumption, frequency will go up. Yeah, this is the principle. And what we try to emulate also in microgrids is to emulate this principle. Yeah. So what we do is we create a control system, which you can imagine that have 3 layers. Yeah. It's very interesting also to see these 3 layers of control, how we have a lot of 3 layers also in our body. No? When we talk about digestion system, the heart and the brain, yeah. And then when we go inside the brain, reptilian level, limbic system, and the cortex. Exactly like this, you can see on how our big power system work. If you look on big power systems, what you have is primary control, which is basically all the inertia of the system. That means that there is a reaction when active power, for instance, increase, frequency maybe decrease, and vice versa. Yeah, this is very reactive. I will say like reptilian brain, right? If you try to bother a snake, you will see the reaction. It's very fast. Then we go a little bit higher level because we see that, for instance, the frequency is going up. Then this means that I have a lot of generation. Then this means that maybe I have to start disconnecting generators or to add more loads in order to balance it. Or vice versa. If I see that the frequency is going down, then maybe this means that I need to increase the generation or to disconnect loads, yeah, in order to balance and to have the frequency back again. This is a little bit slower, yeah? And we could think that this also corresponds to the limbic brain. And then we have another level, which is the tertiary one, which is trying to, okay, let's try to schedule generation and loads for maybe day ahead and to optimize the whole system. We are able to go into the future and see, okay, I'm going to have this amount of generation according to the previsions, and then go back to the present moment and take decisions. This is exactly what our rational cortex is doing every day. Right now, you are predicting, for instance, what will happen tomorrow, and according to what you are predicting for the future, you are taking the actions now. So I will say that this is really useful to also understand our brain functionalities, to understand also how the electric system works, right? And now if we look at that, when we think about a microgrid is just a small scale electric system. So we could also apply the same idea, and this is what we did. However, as we don't have inertias, in the primary level, we have to add those inertias with local controllers. In the secondary control is a little bit different because active power, when you go to more resistive lines, is more connected to the voltage than to the frequency. So here, the secondary control needs to take care not only on the frequency, but also on the voltage. And then the tertiary control, because it's a smaller system, then we need faster reactions. So this means that this kind of energy management systems needs faster response than when we are talking about big power systems. And this is because you have very reduced inertia. So then, of course, the bandwidth of these controllers is reducing when we are going up, but still this system, the whole control system, will be faster, much faster than when we go to big power systems. And this is a challenge. A second challenge is like, because we have very small systems, we could have larger variations, and it's more difficult to make predictions and also to average according to some stochastical models. And this is something that we can talk also later. This is just one example about the frequency secondary control in the north of Europe. And you can see that here we were inside these limits, around 50 millihertz plus minus is still okay. But when we go down from these limits, we need to restore the frequency within this speed. In that case, it's 900 seconds, but because it's a large power system. And then if we are inside this, then we don't need to do anything. So this is kind of a dead band. And then this is kind of a PI control regulation, right? It's a little bit more complex because but you can imagine that this could be in a centralized SCADA system, just measuring the frequency in one point of the grid. It doesn't matter where you go, you will sense the frequency. So that's something very nice also. So this means that our primary response, this reptilian action, is more changing from this frequency point to this other frequency point when the power increases. And the secondary response, what we'll do is we'll see, oh, my frequency is going down, so maybe I will increase the generation, and then I will restore the frequency towards the initial point. This is how it works. There is, of course, two ways of implementing this. One is to have it more centralized one, because we can measure frequency in one part of our grid, and then we can send to all the units the references of frequency to restore it, and maybe to increase the power generated if necessary. But you could also do this in a distributed way. So this means that all your units could have local controllers, and they will share the information by means of communications. There is not a better one, indeed. Some people may think, this is better, the other is better. No, there is no better one. This solution have a problem, which is if this SCADA system fails, then the whole system fails. The second, maybe one of these units fails, still the system will work. However, you have a lot of communication issues between those systems, and maybe could prompt to instability if they don't agree on the final outcomes. So that is not a perfect solution. Indeed, hybridization is a very good option. So sometimes we have SCADA systems, and then sometimes I have distributed controllers which could talk each other. You know, there are some communication systems, especially field communications, like CAN devices. If you think about CAN, or, well, there are many others that you could use for that. Then this brings us to these two solutions: more centralized one or more distributed one, right? And this means that also, because we have this kind of hierarchy of the control of microgrids, we could have that each of our microgrid system could have their own controllers. And then in the top of that, we could still build SCADA systems that could make, for instance, our microgrids to operate when they are connected in the same area. So that could bring us that we could have clusters of microgrids interconnected between them. And then we could also interconnect some other clusters. And we don't need to destroy all the things that we did, because we just send, let's say, the references from a superior levels to our SCADA systems. Yeah. So that means that we have kind of electricity or power exchange connections, and we can have also data exchange connections as well. Normally we think about higher areas, then maybe sometimes it could be internet, or it could be many others. We can discuss this later if you want. So that is basically the three-level control that we have normally in microgrids. And of course, it's very important to link these things with smart meters. If you want, we can talk later also about smart meters, but it's very important to see how smart meters, it's not only information that goes to the utility, but we could also use locally, let's say, for our microgrid system. The other interesting thing is also about power quality issues. And here is very important to take into account this whack-a-mole effect. Whack-a-mole is a game very typical in Korea. So you just, when a mole appears, you just walk it, and then appears in another place of your board, and they get crazy just walking the mole. Yeah, this is what happens when you try, for instance, to compensate harmonics in one part of your grid, then it appears automatically in another part. And of course, in life, it happens a lot. Engineering life, yeah, you improve something, and then something else pop up. Yeah, that's the whack-a-mole effect. Just to give you an example, this is also from Japan. This is the microgrid project placed in Sentai. So in that case, we have a number of photovoltaic panels, and there is also fuel cells here and a couple of gas gensets. And this facility is very close to Fukushima. I will explain you also something about this. It's a very symmetric thing. So we have photovoltaic systems. And then this means that we could have, for instance, DC-DC converters connected to DC buses and connected to DC loads because it's connected to communication systems, but also AC-DC and DC to AC. It's kind of very, very symmetric thing. What happened the day of the earthquake in Fukushima, this is now 10 years ago, exactly 10 years. It was really terrible. And was even more terrible what happened with the nuclear plants. So this is also a sign to say, are we going to continue implementing nuclear plants? I will say no. We want to promote renewables, and I think that it's very important that we, the people that work on engineering of renewables, are convinced about that. Yeah. This is just one example of what happened. Okay, it's in 2 days. It will be the 10th anniversary. Yeah. March 11, 2011, yeah, in 2 days. You see, here it was the earthquake, and then at that time they go totally disconnected from the grid, and Microgrid was just powered with batteries and photovoltaics. And then the natural gas engines were reconnected here, so it was 2 more days also working on in island. This Microgrid is connected to a telecom station, so people could call home and so on, and also to a hospital. So the hospital could still work. You can imagine that was very important at that moment. Yeah. So yeah, just a small example of how renewables sometimes has to deal with disasters, which are also connected with some other terrible things. Yeah. About if we go to DC, it was a lot of discussion to see if we can have also DC at homes. And I will say this is not happening, but some products are coming, for instance, to place in some places. For instance, this is a product that is being sold in India to have, in that case, DC microgrids in the level of 230 volt DC, and you can transmit over 1 or 2 kilometers the power. And then we have the bipolar thing, which is basically microgrids that could work on plus, minus, in that case was 170 volts, but right now we have also higher microgrids going to plus, minus 800 volt, for instance, in Finland. And it was commercially available, this idea, but right now it's more like, yeah, it's more like an open standard. And they are using the same principle of frequency, let's say, but in voltage, because it's a small microgrid and it's a DC one, then what we see is that the voltage is increasing when we have more generation than consumption, and vice versa. And you can see very similar things also happening, for instance, with aircrafts. This is a hybrid aircraft, the 787. It has some parts on electrical, but right now there are some prototypes and they are moving to have also maybe full hydrogen aircrafts. In that case, it's only some small wind turbines here and some of these distribution systems which are really microgrids. So generation in red, AC microgrids in the level of 230 volt, and then AC microgrids plus minus 270 volt on DC. So that's, I will say that this is amazing and it's impacting a lot. And then let's move to the last part to show you some examples on microgrids in space. Yeah, we have some also work on ships, electrification, and so on. But here I'm going to show you some of these examples in non-satellites. So this is a collaboration we have with this company, ComSpace in Denmark, about nanosatellites. It's very small satellites, which you can see you have solar panels, battery systems. In that case, we have lithium ion, the same that you have in electric vehicles. And here the impact is that you have a lot of pulsating loads. So these loads are basically electronics, high-speed communications, and what we call also payloads, so cameras. And then you can see here, this is how it looks like, our microgrid. It's really small, a couple of battery systems. And then we have also boost converters, and then a number of regulators. Here, what is really amazing is that when you are out of in space, you have a lot of radiation, especially protons. So because here in the Earth, we don't feel that, because we have the atmosphere, and we have also the magnetic field of the Earth, which protect us. However, out in space, you have a lot of protons, and also because you have solar storms also. This gives a lot of cosmic radiations, which will impact battery systems and also photovoltaics modules. Right now, we are also studying that, how this is impacting the photovoltaic system. But another important thing is microprocessors, because if you put all your algorithms inside a microprocessor, due to the cosmic radiation, you will have a phenomenon which is called latch up, which means that that all the digitals are based on CMOS. So your CMOS maybe will be latched to plus VCC to 1, and this means that your microprocessor will be hung up. So it's very important that all your controllers are analog. So analog controllers are being implemented in satellites. Maybe you can think that is funny because we are talking about technologies of decades ago, but this is right now what we are doing in satellites. So microprocessor is more like a supervisory control, and all the controllers are analog inside. Yeah, and another important thing is that in a satellite you have eclipses very often. Yeah, and you could think, okay, why? Well, because you are just going around the Earth. So you can see that here you start an eclipse, and then here you have sun again an eclipse, here you have sun again, and so on. So you could have everyday eclipses. And this is very important to design the battery system and your whole system, because it's really affecting a lot. You will have connections directly from the sun, in which you have a lot of power to be exchanged with the payloads and the battery. And when you enter in eclipse, you just have all the power coming from the battery system. Just one example, this is from a CubeSat in Finland. And you can see here why it's called Cube. Yeah. And in that case, you have here the solar cells, and was launched in last year, in 2020. This satellite was using 2 payloads. One is the particle telescope. So in that case, we wanted to measure solar radiations. So just to measure that. And then we have a plasma break also here. And these two loads were supplied by this telescope. Here you can see the electric circuit. So here you have the MPPT charger. This is normally, for instance, a boost converter, but you could have other topologies. All of them controlled. And then we have here the DC bus. Here are the different payloads. And then we have the battery system as well. Yeah, connected here. You can see here the main subsystems. So we have this particle telescope. We had also the electric power board and the camera and the magnetometer and so on. Also radio communication system. Yeah, and it was 6 loads was regulated 3.6 volt. So it's really low voltage. Another example we have here in the International Space Station. So here you have basically all the solar panels and antennas here. I'm going to show you how it looks internally. We have the battery system and the photovoltaic panels. So here is basically generation and storage. We pass to 133 volt till 177 volt. And then we pass to the secondary power system, which is basically consumption. So we have here separated generation and consumption. And right now, with a number of converters here, it's fully operating in DC. In the past, the International Space Platform was only using AC, but it has been changed to DC. And then to finalize also some work we are doing right now with lunar-based microgrids. Right now, a lot of people is looking at the moon, and I think that this is what is really coming. As you know, NASA is coming with the Artemis moon mission for 2024, in which they want to return astronauts to the moon and to have a small station there. Also, we have from the Amazon funder also, we have also the Bezos project. And then we have also, of course, SpaceX coming also with the land Starship on the moon before 2022. And then to have cargo runs in 2024. Yeah, we'll see how the things are ongoing, because maybe recently we had some explosions from SpaceX, but this is just, we are in the test phase. Japanese are also coming with more idea. The JAXA space exploration also. And of course, China having also preparing to have more main moon landings. Here, the idea is that if we want to have a lunar base already available, we need a period for starting putting more and more people, like first starting 3-4 people, then around 10 people in 1 year, then between 10 and 100, and then going higher. No? So this is an idea of project in the next 15 to 20 years. It's a long-term one. Then if we think about a lunar base power systems, you have power generation. And when we think about power generation, this is really like a microgrid, you know, we have generation, we have storage, and then we have load and power management system and distribution. So we have possibilities of having nuclear fission, yeah, like a reactor. There's recently some people are talking about that. And then the other is talk about electrostatic charge, because the moon itself is already having some charge and we could use this electricity. However, this idea is still in very low levels of applications. It's just in laboratories. So we are far away still. And talking about nuclear fission, really, we don't want to go there. I know that a lot of people are talking about that, but please, no, we don't want nuclears in the Earth. And of course, we don't want this in the moon, right? So for me, it's out of discussion. And of course, it's expensive, but we don't, I will say, I don't care if it's expensive or not. It's really hazardous. So it looks like the real hope for us is solar energy. Not hazardous, convenient, relatively light. So we have more and more light solar panels, and it's an already tested technologies for many, many decades. Yeah. So future in the moon, it's really in the sun energy. If we look on the different possibilities, we have the dark side of the moon here, which is called also far side, and the near side of the moon, right? So there's a number of places in which we could think to install those things. One of those places was, for instance, the Peary crater in the North Pole, in which also it seems that they found some water. So it could be a good combination. No? And of course, we have to take into account the light also, and also that we have a low declination angle. So we talk about 1.5 degrees only. We have little elevation in variation in solar elevation also, and there is a continuous available through all the year, right? So here the problem is that we have steep terrain at the polar regions with a lot of craters, let's say, and we have transitions to sunlight regions like more than 15 days, or then we have with low terrain less than 15 days. Yeah. And then when we talk about the non-polar regions, sunlight and dark periods are around 15 days each. The eclipse can be about 5 hours twice a year due to the Earth. Yeah, so the Earth is just in the middle between the sun and the moon, and then we have to also take into account that. So we have basically two polar regions interesting right now. One is the South Pole, which is also called Shackleton crater. There is one crater that already has been studied a lot, especially NASA had a lot of interest in the last years. And the other one is in the north, which is called the Peary crater. So here you have a picture about the Peary crater. And this other picture is about the Shackleton, this one, right? So the first one, what we have is few locations which receive continuous sunlight, and then we need a tower of around 100 meters to reduce energy storage. So yeah, and there's some challenges. And the other one, the Shackleton one, is one of the most illuminated locations. We have an average irradiance of around 86% and receive continuous light for 6 months. So I will say it looks a very nice location also. So it really depends, the power generation, it really depends on the location and the site, yeah, and we have to study it. The other one is about the energy storage system we have to select. So because we have these frequent shorts of illumination and darkness periods, then we need energy storage systems that can be recharged in the short illumination periods, and to reduce as much as possible the size and the mass, of course, because we at the beginning we will need to send it from the Earth. So those are some of the specifications: high specific energy, long life, of course, long cycle life, and high specific power. One of the possibilities is, of course, to use batteries, and the other is to use regenerative fuel cells. Yeah. So those are the two technologies that are being considered here. And when you think about regenerative fuel cells, means that you have hydrogen coming, for instance, from electrolyzers that you could reuse. And we could also have, for instance, in the future, pipes of hydrogen in the moon. Yeah. So we made also a comparison between these two elements. And it looks like fuel cells are going very well. However, especially because of the massive amount of energy that you can store, very light, but of course you have less efficiency because you need to produce hydrogen probably from electricity, which is very non-efficient thing. So finally it looks like it's going to be a hybrid what we are going to have. Here you can see simulations for 1 month illumination conditions of the Shackleton crater. So this means that if we need to put photovoltaic systems, are going to be here in the more upper part of the crater, not inside, right? So it's on those areas. Yeah, again, it's also very dependent on the location and site when we talk about energy storage system. And about the loads, what we will have is the crew habitants inside, which will not be crew anymore. It's more people living there with all the appliances. And then we are going to have also laboratories and exploration, which have some special loads. And then we will have also in situ resource utilization, because we will have to create some of the things that we're going to use there. Yeah. So imagine that also we will have to generate hydrogen, and also we need e-mobility. You can imagine that diesel or other things, gasoline doesn't work, which is also good, but you cannot basically have an explosion motor. Yeah. So it's really a place in which no more excuses to go for 100% renewable energy, right? So maybe we are going to learn a lot from that. And then here we made also about the power requirements. So we made a study about which are the power requirements that we are going to use in this lunar-based microgrid system. And the other thing is about the power management and distribution. So of course, when we think about that, we are inside the Earth and we have satellites and we have communications, we will need something similar in the moon. So if we have to rely on the communications between the Earth and the moon, it's going to be very hard, because many things are going to happen here and we need real-time communications inside in order to balance, for instance, power, hydrogen, maybe flux, and many other failures and problems that can occur. And that's why we are going to have to be more, let's say, autonomous from the Earth. Of course, we need communication, but still we will rely on internal communication. And in that case, reliability is crucial, and the human from the Earth intervention is going to be very difficult. So we started with single microgrids, but now we see clear that multi-microgrid systems will be needed in the moon, especially if we are going to need to have different sites to be also interconnected between them. So you can see here our objectives when we look on multi-microgrid systems is also connected to suitable locations, sizing of solar panels and energy storage systems according to which is the camp. And then what we are also studying is which is going to be the architecture which is more reliable, which even you have 2 points of failure, still this could work. Yeah. If we think about the Shackleton crater and we need to put some PV panels outside, and then we have some connection to the lunar habitats. We have some connections also to the laboratory stations and the charging stations, which are necessary, and also to the labs. Then, of course, we will need to build telecom infrastructure for them. And we are going to have a number of zones that finally they are going to be interconnected between them. And this is a very clean way of starting microgrids from scratch, from the needs that we have, because we know that all these different zones are not going to be started at the same time. So probably we are going to grow from zone 1 to zone 3, and this is a very natural way. Yeah. Then I would like to finalize. I know that I'm a little bit out of time. I don't know if I have to cut here or.
Yeah, I think we are okay with that, because we need to finalize the presentation by 11. So I think we have 20 minutes to have questions. So
all right. Thank you.
So I think.
Thank you. So I just let me finalize with another example. And in this example, what we did is a collaboration with the European Space Agency and the University Autónoma of Barcelona in Spain. And in that case, what we did is all these ideas that I explained you about the 3 levels of control in microgrids, we expand to what we call space closed ecosystems. So we expand the microgrid concepts to what is called also bioastronautics. I'm going to explain you a little bit this. The idea is that if we are going to have, for instance, a base in the moon, we will need to also create our own ecosystem, because it's not possible that we are sending all the time food to the moon, etc. So we have to create a small ecosystem there. If we want to create ecosystem, for instance, I know that there are some places in the world that they try to create ecosystems, but they are doing from the principle to generate an ecosystem for another planet, which is really something difficult. And here in the pilot plan of Melissa, what they are doing is to create an ecosystem just to go to the International Space Platform, or to go to a small base in the moon, so that you can feed the astronauts or the people living there with oxygen, water, and food. So that's the idea here. Melissa had a number of 6 microbiological compartments. So we have the people. Don't forget that we are biological also. We have the waste. Yeah, maybe some food. And of course, we need to make, also we have our, we are also generating waste ourselves. So if we think about urine, it's possible by using a photoelectrophic, we can generate ammonium. So it's like at the same time that you go to the toilet, you can also generate ammonium. And then those ammonium are really interesting, because You could generate also nitrate, which will need some oxygen, and then we can feed microalgae. Then from the same compartment, we can also feed with CO2 to higher plants. And then we will take also some CO2 from the waste for these higher plants. So basically here, those higher plants are taking out the CO2 and converting to oxygen thanks to the photosynthesis. And then also our crew members can eat those higher plants. So we are also generating food and at the same time water. So here the astronauts will have food, water, and oxygen. We'll take out the CO2. And the only thing that we need here is, in order to make the photosynthesis, we need light. So again, we have sun power here. But it's a disconnected system. You know, it's an ecosystem which is disconnected from any other kind of ecological system. So it's really a microgrid if you think about it. And this was our idea, to think that this is really a microgrid. You can see here a picture of the nitrification compartment, the photobioreactor, the higher plant compartment. And right now the test that we are doing is those mouses, because of course we still didn't pass to the human test. And I think that this is really interesting because we need to regulate especially the oxygen in a very tight levels of around 20%. Otherwise, if it's very high, we will kill the people here, or if it's very low, also you will kill them. So you need to have it very tight. And what we observe here is, in this number of compartments, even if you think that this is just a closed loop system, you have hundreds of state variables, hundreds. So it's very difficult to control, and at the same time is highly nonlinear. So it's not like having this kind of systems that you have maybe a number of equations. Is really exponentially increasing the complexity. So here, in order to organize the control of this, what we identified is that there's a clear parallelism between closed ecosystems and microgrids. And it's funny because at the same time, the only thing that we have external, the energy external, it's just the sun. So it's kind of the same, no? So when we look at the photosynthesis, we could assimilate to photovoltaics. We have also a compartment to store oxygen. And in the microgrid, we have energy storage systems. And then we have biofuel cells. And in microgrid, sometimes we have hydrogen fuel cells. So what we did here is we make a parallelism between these two systems. And we applied a 3-level control, trying to translate all the things that we learned in the past from microgrids, in which we have the primary level for voltage, current regulation, and power sharing, the secondary for voltage, frequency restoration, and the tertiary level like energy management systems. Here, the primary control, what we did is more mass flow regulation. The secondary control, what we realized is that some of these flow mass had some steady state errors, which we could correct with the secondary control, and also to arrange flow dispatching. And then the tertiary level, the same way that we have energy management system for microgrids, here what we did is a long-term optimal operation by setting points to the entire plant. And I think that this is really amazing, because what we are doing here, we are using a control structure that has been used for electric systems and translate to a ecological system. Yeah. And finally, yeah, we did it. Sorry, we did it. Here is the pilot plant, and here is our laboratories in which we develop the controllers. And you can see the plant. We call the oxygen tanks, also the photobioreactor, and so on. In the primary control, what we had is PI valve controllers, and also the control of the light, and the tank controllers. And in the secondary control, what we had is some, let's say, based on model predictive control, some objectives and constraints in which we send back to the primary control. So basically optimization of valve and tank schedules and flows, and also to optimize the oxygen in one of the compartments. And then in the tertiary level, it was fully optimizing the system. So that also was based in that case on a model predictive and having a lot of these optimization algorithms here running. So we had really a reduce of bandwidth when we go up from the primary to the secondary to the tertiary control. We also observe some parallelism when we control some of the variables on electricity, like frequency or voltages here in our biosystem. And then in the more higher thing, we had also supervisory controller. So finally, we were able to control on the system the oxygen concentration. And these are the oxygen also in the tank of oxygen. It was very similar as a controlling a battery system, yeah? The state of charge of a battery system. It was really interesting, I think. And I think that's all from my side. I just want to finalize with a statement from Albert Einstein. He said, we cannot solve our problems with the same level of thinking that we create them. Thank you.
Thanks, many thanks for your great presentation, interesting and very entertaining presentation. So it's actually amazing how we can connect with all the brain and our body, and how this kind of connection could create some advancement in the way we are optimizing our system. So I think machine learning is still in the beginning, and we could actually enhance their performance in the future. So I have here I will start with some questions that I got on the chat side, and then maybe I will open the for anyone who wants to ask his question. So for sure he can activate his microphone. So I will start with the question of Nicola. The question was about, do you think that the implementation of microgrid could help energy self-sufficiency? For example, when we talk about islands, and I mean the fact that we are using, I think, let me just precisely, if the island is generally used in renewable energy sources, especially solar energy. I guess he meant that it depends on the local renewable energy sources available on the island. How we make sure that all the renewable energy sources are available to supply the load that is available in this level. I think your microphone is should activate. Yeah.
Yeah.
Yes. Okay.
Yeah, that's a very good question. Of course, it depends on the location. But I will say that the key point here is to make a proper planning of the system. So you can size your generation, and you can size also the storage. And then you size it according to how long the time it will be without this resource. And then you can also do some backup.
And I think the time where we don't have, like the worst case scenario where we don't have no sun, no wind, and we have only the battery that is as a backup that can be used. So I think, yeah, there is a compromise that should be done. Yeah, and just talking about the practical cases, do you think that we can in all your cases we can fully use the renewable energy sources, or we can also add some diesel generators or some other sources that depend on the fossil fuel?
Yeah, I think that's very interesting. I think that the fossil fuel has been used as a backup.
Mm-hmm.
But,
yeah, exactly.
But today we start to have backups which are renewable, like hydrogen.
Exactly, yes, long-term storage.
We could think about this. And the second thing is that if we think about that, we could interconnect microgrids, so we make the system bigger. Then you could compensate sending back and forward. That's why, connected with the first question, if we are able to interconnect areas based on renewables, we can finally fulfill 100% renewables without using extra fuels.
Exactly. And also one thing very important, I think the demand response could play an increasing role in the design itself, because it's a kind of flexibility that we can add into our design. So we can allow that we can curtail some load in some cases, some acceptable load for the consumer viewpoint. And in that time we can actually balance between the load and the generation.
Yeah, there is something very interesting here, because many times microgrids are also connected to loads, which are heat or cool loads. For instance, freezers, big freezers like we have, for instance, in the Nordic countries with fish. And you have really an interval in which you can work. So between two temperatures, it's fine. So then this means that you can connect or disconnect these freezers.
Okay,
Finally,
yes,
what you have is storage in terms of cool.
Exactly.
And it happens the same with heat. So we have a lot of industry that is using heat. And then this heat can be also a shift along the day.
Yeah, it's like phase changes, you know, you can use exactly.
That's why what is called right now P2X applications are becoming more interesting, because it's something that the industry needs, and we'll have more incentives, for instance, in the Scandinavian countries like Denmark, to the people who are dealing with the P2X. It's not like a small house, you know, because when you talk about a single house, demand response, it doesn't work. We know that it works when we talk about big industry.
Yes, exactly. Yeah. But also one thing very important talking about island is that we can use the desalination side, because we have the sea and we have also another kind of renewable energy sources that is available. So I think mixing many renewable energy sources would have a different behavior could lead to a balance between. For sure, there is a compromise with the price, but I think if we are talking only from reliability viewpoint, I think this can realize some balance. Yeah.
Yeah, exactly. What you say is precise indeed. A lot of applications of waters are connected with energy many times. So especially things like desalination, which you could shift from 1 hour to another. That could be something very nice. And we have to start thinking globally, you know, thinking in a holistic way. So we don't need any more solutions, local solutions, which we know that doesn't solve the problem. Yes. It exactly happened with also today's medicine. So nobody's talking anymore about that you have one specific problem. Yeah, everything right now, many of these diseases may be connected with some problems that you have with the mind, also psychology.
Yes, exactly. Yeah, stress. Talking about the
we cannot separate anymore. And right now, also in the presentation, I show you we have neurons in the whole body. How we can separate mind and body?
Exactly. So I think it's the way that we should see our Earth. You know, when you are designing a microgrid in Denmark, and what is its effect in Canada, or vice versa. So I think it's important to analyze the effect on the global scale, and this could be a very an interesting thing. So the second question from Jean-Antoine, he said that the challenge for microgrids from his side, the challenges related to microgrids seems really to be related to energy storage system and not to harvesting anymore. So he said, what are your thoughts on the metal usage or use if we deploy many microgrids? Because would we encounter a supply chain problem in the extraction of metal, such as lithium and some other elements that we are using in the microgrids?
Sure, we will find challenges.
Yeah, so
but we cannot continue as before. I mean, we cannot continue as before. So we have to find challenges, and probably we will have to solve it again and so on. But we have to, I think that we have to do it in the way also, maybe the problem, and now that you talk also about the Earth, we feel some disconnection from the Earth. You know, we feel that human beings, we don't belong to the nature. We don't belong to the Earth. And indeed, we can see the Earth as an animal, let's say. It's our mother. So it's very important that we feel connected again. Yeah, feel connected means that if you analyze also your blood have metals. And these metals are coming from the Earth, and these metals from the Earth are coming from the stars.
Exactly. So all these.
So somehow the problem that we are having is like we are right now. Maybe those metals are concentrated in some parts of the Earth, and what we are doing is we are scattering them. Once you scatter them, you cannot use them anymore because you will need a lot of energy to put them together again.
Yeah.
So what we have to do, and I agree with you, with your question, is that we have to try to be careful of what we are going to scatter next.
Exactly. Because that maybe after years we will say, oh, we'll be back. I know what we have done, and then everything should be planned in a smart way, so we can, in a sustainable way. I think maybe this is the word, in a sustainable way, so we can make sure that what will happen in our future. Another question from Mahamadou. So he said, what do you think? What do you think about taking into account the consumer's behavior in the microgrid, generally in terms of in the space one? So once we are talking about, it's a good question. Once we are talking about space microgrid, how we behave, how we can model actually the behavior of because the starting point to design a microgrid is actually to see the behavior of the consumer, to have a profile of load. So in this case, how we can model this kind of behavior?
Yeah. I think that we are learning from the International Space Platform, in which we have people working in turns. So it's kind of very flat in that case. But of course, when we will go to the moon and having a base, maybe we will have different behavior, and still we don't have the data. So yeah, it will be something very important also to take into account. Totally agree with the question. And probably we'll have to define a new schedule for the people that will go to the moon.
Exactly. So everything will change. We'll start from zero. So we'll, all the behavior will be changed. Okay.
There is a very interesting experience in Chile, in a small island. It's called Huatacondo Island, and in this Huatacondo Island, they have no electricity from outside, so PV panels and batteries, and they realized that very fast the batteries were running out, and then they train people to use the electricity. They call this social SCADA, because maybe you think about very fancy things that in a laboratory will work, but then in practice it will not work. I think that this is not something, but they come with this idea, so we will train the people, and then
after that we can exactly. So another question from Maxime. He said, what is the main component of microgrid that should be technically improved to help development, commercialization of microgrid around the world? Because we know, I mean, from my point of view, I see all this benefit from microgrid, but still see that in the world we have limited implementation of microgrid. What I'm talking about Canada, it's actually we still develop some microgrid, maybe at the campus level, sometimes at the some urban scale, but still that what will be the motivation actually to change to make everything a microgrid? Because I see it from the urban scale. If you talk about city, every microgrid or a number of microgrids could be connected to a urban microgrid. They can even talk together with the different microgrids. And what is the challenges part in terms of the implementation of the wide implementation of microgrids?
Yeah, that's a very good question. You see, when I see countries like Canada, I can see that you have a lot of hydropower.
Exactly. Yeah.
And itself, it's renewable resource. And it's very good because this means that you can implement a massive amounts of renewable energies. So, so maybe you have to think about that the microgrid concept, not as a small wind turbine and a small PV panel, is maybe to think about how you can start interconnecting offshore wind farms or large amount of generation, because you really have a big, very big battery system.
Yes, exactly.
So, this is introducing the microgrid ideas into the grid. That means, for instance, recently it was in UK a big blackout because it was a disconnection from a central plant, and then the frequency started to go down. And then the offshore wind plant, so the frequency is down, I'm going to disconnect also. And then they create a blackout. Maybe what we have to do is to create systems that can integrate more renewables. So thinking on that side, so no one else will come and they will say, oh, don't worry, I will put we need coal plants, or we need any other kind of plants because they give stability to the grid. we can demonstrate, thanks to the microgrid principle, that we can have the grid stable without these kind of old power plants that we don't want them anymore. So it's more maybe the transformation on the grid side, no? And I can tell you that if you think about the microgrid more in the concept of small grids, we see this in places like for instance, Ethiopia, in which we are making a project to put a microgrids there, because really there's a huge amount of the population without electricity access.
Yeah.
So then the first initial thing was, okay, let's put solar and diesel. And we were a little bit astonished because you say, okay, let's try to don't create more problems, right? So it's more to create those microgrids when it is needed. Or for instance, another project we are starting right now, it's to create microgrids in Indonesia, because there are basically a lot of blackouts because of the number of storms. They have everything imaginable, storms, etc. So then you need more resilient systems, and they can be also disconnected from the grid. But when you think about grids which are very stable, like you have in Canada, then maybe it's to think how you can improve the penetration of renewables and go targets to, let's say, in this year we would like to have 100%. What we have to do, and then make people to understand, yes, we can go 100% renewables, because still some people, even politicians, thinks that 100% renewables is not possible.
Yeah, no, I think it's in Quebec it's possible, but I think talking about the transportation also can play an important role, because here maybe in Quebec the greenhouse gas emission is coming mainly from the transportation and from some industrial sectors. So I think we are starting to actually plan many charging stations so we can move to the electric transportation, because we are going to benefit from all this hydropower that is available. But coming back to the question that what is the motivation, maybe in different parts of the world we should analyze the problem of the utility before we're talking about a microgrid. Here, for example, in Quebec, we have problem related to heating in the winter, and we have a peak. We have a peak problem in the grid. And peak problem, we have some problem in the transmission sector, congestion, some other kind of problem. So if we are implementing this microgrid, we will be able together to shave the peak and to maintain the stability on the grid. So I think maybe the contribution here will be more on the reliability side, and also because talking about having microgrid will help the utility to look for some other new markets in the United States, because in this way we can allow some exchange, maybe with California, maybe with other states that have some issue on the greenhouse gas emission. So we are contributing to minimize the greenhouse gas emission from here, because we allow the reduction in the emission from other places. So I think it's a very potential, but I think the coming motivation, how to motivate people to implement microgrid and even to implement PV, because the kilowatt hour, the price of kilowatt hour here in Quebec is very, very cheap. I think it's even from 5 to 9 cents per kilowatt hour. So it's very cheap. And people, they said, I'm ready, I can pay for that. So I think we should work hardly on motivation side from the consumer's perspective. I think this is well, let me see if we have some other question. Yeah, we have some last question. I'm wondering what is the biggest energy used in place, like the moon? Plug load or heating cooling load? To bounce off, okay, this is, will thermal mass storage be sufficient option to compensate for the lack of metal supply? So I think this is the same person who asked about metal supply. So yeah. So this is my last question for today. Yeah.
Yeah, it's about, of course, heat will be one very important consumption that we will face there, because you have to imagine that we have very, very low temperatures, especially in some places, but in some others also the temperature can rise a lot.
Yes, exactly.
So it's really complicated. So I don't have the answer for that now. We have some numbers, but I don't have the final.
Perfect. Perfect. I was wondering if the audience have some other question. Maybe you can activate your microphone if you have some question, or you can.
Yes, Professor.
Yeah. Yes.
Yeah.
Hi, Ahsan.
Hi. Hi, Professor Joseph. My name is Ehsan Razai. I'm a PhD student working with Professor Dagdougui on the network of microgrids. So it is really similar to actually what you present here. And first of all, thanks for your interesting presentation. It was really helpful, at least for me, especially the space microgrids parts, when you explain through a practical example how we can design a microgrid and what we need to consider. So I have several questions. I try to ask them really quickly. My first question is that is there any guideline or, from perspective of a system engineer, is there any book that can help us or leverage us to when we try to design a microgrid, for example?
You mean some tools there? Yeah, because it's a very complex thing. You need some specific tools. So you have from private tools like Homer and so on. But the problem of Homer is that they come and they don't consider the operation. So it was the question also that I put to the CEO of Homer, asking, are you going to have a link with Simulink? They say yes, but I know that it's very difficult to have it because, yeah, it's complicated. So it's like chicken and egg problem, no? You design, you make a sizing, but you have to consider the operation, and then the way that you size, it will affect the way that you operate, no? So I understand that is complicated, and there are other tools, like there is another one which is called OMG. It's like an open microgrid, like oh my god, yeah, OMG, which is an open source tool, also trying to make sizing. But I think that we don't have a definitive tool, and this is also because microgrid cannot be defined. So maybe you will have to come with a tool for a specific applications of microgrids, probably.
Yeah, exactly, because we had this discussion with Professor Dagdougui that the operation, the method that we use for control and the operation side can affect the sizing problem and vice versa. So it is really complex, and I don't know, maybe a nonlinear problem. It is really difficult to, at least, yeah, exactly. And so my other question is about actually, I found you have implemented a lot of projects and a lot of interesting projects around the world. My question is more technical about the control side. So far, I saw in your presentation that you implemented, the traditional actually strategies and controller. So I'm just wondering, have you ever tried more complex optimization problems such as MPC or stochastic model predictive control, or I don't know? And if yes, how much it was practical, and what were their effects on actually, for example, frequency or power shading or whatever?
Yeah, in general, I will tell you that in major part of the projects we didn't implement those things. So the simple, the better. And about MPC, you could have some possibilities. For instance, in the case of Melissa power plant, we implement MPC, but I think it's more because of historical reasons. So they had a lot of models, and they need to implement. And then it was, there is something else called PFC, but I will say that this is a kind of a PI controller modification. So yeah, I will say that that except sometimes when you try to model some loads and to have some idea of how are going to behave the loads, probably with MPC, normally I try to use as simple as possible methods right now.
I think it's from a practical viewpoint. I think it's already it's good that we have implemented microgrids. Maybe the MPC or maybe many other kind of approaches. It just I think the question of Ehsan said, he said whether we are we don't have any barrier to enhance the optimization problem from a practical viewpoint. So
yeah,
because,
exactly.
Yeah.
No, I think that is very good to think this way, and we don't have limits, as you say, but sometimes computation time is a limitation, so we have to consider this. And sometimes some people try to apply very complicated controllers with something that you can solve just with a PI. But maybe when you need to, for instance, optimize the energy of a system, then of course you will need tools that are maybe more advanced. And I'm open to try all these tools if I can see that the results are really much better. Otherwise, I will try to be always with a more conservative solution. But just because we are working very close to the real plans. So if you give me a very nice solution, I would like to see at least that this solution has been tested for a number of years and number of applications, and it can be reliable. If it's very nice in a laboratory, but then we try in our plant, on our real plant, and we have complaints, then I think it's an issue. So I think it's because we are working at very high TRLs. So, and I understand that some other people has to also be there developing, and there's a very good, I think, understanding, because we are trying also many ideas from different researchers in the world, and I think that universities are having very good researchers with very nice ideas, and our center tries to be a complement to try to put some of these ideas to the practice, and this is something that of course always takes time, no? And you have to deal with two walls, no? One wall which is more ambitious and try to develop something very, very new and fantastic, and another wall would say, okay, very good, but I have customers here connected, and this have to be running for a number of years, no? So, and we try to be a little bit in the middle, no? Yeah.
Perfect. Anyone else have some? Thank you, Ehsan.
Thank you, Ehsan.
I think Alexandre, one last question. Sorry, this is the last one, so it's just to.
Yeah,
that's okay.
Okay.
I could ask if you prefer.
Yeah, sure.
Okay, so hi, Professor. Thanks a lot for the presentation. So my question is a bit more, well, touches a bit on maybe the economics of the microgrid, but it seems like a centralized and integrated management of the microgrids within a grid makes a lot more sense technically than decentralized management. At least this is what I gather. But I was wondering about your thoughts on a scenario where there is a cooperative but decentralized management of microgrids with, for example, a scenario with an electricity free market allowing microgrids to freely sell and buy electricity at a market-based rate. So essentially, the grid becomes like an exchange platform, a bit like a stock exchange or something, where people could trade electricity on a fluctuating market rate depending on demand and supply at any given moment. So I don't know if the decentralized management, what are your thoughts on that?
Yeah, well, what you are talking, I think it's, you are very correct. I didn't want to say that centralized control works better, but I just wanted to show that, for instance, when you talk about more automatic control, some, for instance, the secondary control, we implemented some secondary controls which are decentralized, distributed for a product which is right now in the market, but it's very, very simple thing. So don't think that we are implementing very strange equations. So it's just P and PI controllers. They can talk each other and they come with decisions, very simple. But when you try to optimize the system, of course, if it's centralized, everything goes smooth. Now, what you are talking about is not to have a cooperative control, but I guess that you are thinking more on a game thing. So it's more
it's competitive, exactly.
And then, of course, nobody knows the strategy of the others, and then this is something that is more local. And this is what, of course, when you go to markets, this is what you are doing. And this is exactly what is happening right now in Europe from the beginning of this year, in which the role of aggregator is in every country right now accepted. So this means that everyone can create a power plant and start being inside the market. So this aggregator is a figure that is already approved by law in all the EU countries. And this doesn't mean that we are, let's say, deploying microgrids at all. This means that probably some people that put some generation or even some storage, they can start entering inside the energy market. And this is why a lot of things are ongoing more on virtual power plants. So thinking that you could have the microgrid concept, but in a more distributed way, like some people have some wind farms and adding some storage, which could be in another place geographically, they could enter in the market as a single entity. And this is what is happening right now. Yeah.
And it will be for profit maximization, I guess. They will not talk about load for them. It's just to provide some services to the grid.
Exactly. And now is when artificial intelligence makes sense, because someone needs to make money in an environment which is changing all the time. And you as human being, you cannot take fast decisions. So it has to be someone with intelligence. The same as some people are investing right now money, stocks, and so on by using artificial intelligence. Maybe it may happen with the energy. The point is that right now, let's say that the thing was more easy, like you have a wind farm and you just inject all the power to the grid. And right now it's more thinking when you can sell it to make a better profit.
Yeah.
So I guess that we will see in the next years how this is going to be, because right now we have all the laws just approved 1st of January of 2021, this figure of aggregator in Europe.
I think even it starts here. It's starting as a business model. Right now, it's not in the application side, but I think maybe the case is different in Quebec. But I think the aggregator will be worldwide distributed, because this is the only option to connect between the distribution and the transmission and the production system, and especially the network, the market too, because we are talking about retail market, we are talking about wholesale market, and this kind of market, especially here I think the wholesale market is defined in Quebec. However, the retail market is not yet defined, and this is I think how the aggregator will build this retail market in the future. Yeah. Okay, perfect. So thanks for your great presentation. Thanks, Alexandre. Thanks for your great presentation. It was very interesting, very entertaining for all the students. I hope students will like it. I'm sure that they like the presentation. So from our side, we'll keep in touch, and we'll continue our collaboration for sure.
Thank you. I'm very